Today we're going to talk about logistic regression, in particular how we can go from data to the logistic regression weights that define a classifier. So just to refresh your memory, in logistic regression we have these formulas for the probability of the negative class and the probability of the positive class. And this is an example of discriminative prediction because we're only basing our answer on the data itself. And what we didn't talk about last time is how to actually learn what these beta are from data, so from our x's and y's in our training set. And so that's what we'll talk about today. Okay, so we're going to treat this as an optimization problem, and so in optimization problems you need to have an objective function. So in this case our objective function is the probability of our data. So given some training data, so our training data are x and y, so the labels and the features. Given the logistic regression model, what's the probability of all of the things that we've observed? And so basically, we want to ask for all of the cases, does the logistic regression model give us y's, or predictions of y's, that are consistent with the true y's? So we've taken the log of the objective function, which gets rid of the exp up here, but we still have the exp down here in the denominator. So this is our objective function. It's a little bit hairy, but as you'll see in a little bit, one of the nice things about why we chose the logistic function is that we have nice derivatives here. Okay, so does this formula make sense even if it's a little bit messy?
Yes.
Okay, all right, so this sum over here is over all of our examples, and this sum here is over all of our features, just to clarify that. This is a big sum here over all of these things. Okay, so we want to find the betas that make this function as big as possible. So what we're going to do is take advantage of the fact that this happens to be a convex function. So this is not convex. As we change beta, the function goes up and it goes down and it goes up again. That's not convex, but the nice thing about logistic regression is as we change beta, there is some global optimum of our objective function, and we can use that fact to just walk uphill constantly, and we will find the optimum. Okay, so how mathematically do you walk uphill on a function?
You find the slope or the derivative.
Yeah, exactly. So if you remember calculus, you can think about this as delta of your objective function over delta beta, and we want to just follow the direction that our function is pointing us, and to go where the slope is pointing to higher and higher values of our objective. So you use the word derivative, and so that's a single variable calculus, but in this case we have a multivariable function. So beta is of dimensionality equal to the number of features that we have, and so that could be in the thousands or tens of thousands, or in particularly bad examples, hundreds of thousands. So this is a very, very high dimensional problem. But we'll still use 2D or 3D pictures because we aren't living in the future yet. Okay, so the gradient is defined as a vector where you take the derivative of your objective function with respect to all of the coordinates of the thing that you're trying to optimize, beta, which is also a vector. So you look at the 0th coordinate of beta, your bias function, you take the derivative of your objective function with respect to that. That becomes the first element of your gradient, and so on, up until you get to the very last word in your vocabulary. You take the derivative with respect to that. And so there's still a typo here. Your weight vector, beta, is just going to be updated in terms of this gradient. So if we write it in vector form, we're just going to look at the whole thing. And so we take for each individual coordinate, however, we can zoom in, and we take the previous value of this, and we're going to look at what that gradient coordinate was, and this tells us what direction we should go for this dimension, and we're going to multiply it by a little weight eta, and add that value in. So, okay, so why are we adding here? So why is this a plus sign?
Instead of what?
Instead of, okay, so to ask a leading question instead of a minus sign.
Well, in this case, I guess we're doing ascent.
Yeah, so we want higher probabilities, and if we wanted to optimize to find a minimum of a function, we would go in the opposite direction of the gradient. So in this case, we're trying to maximize our probability, so we have a plus sign here. So we'll take our old beta value, look at the gradient, and add a little bit to this. So this eta value is called the step size, and so this must be greater than 0. And so if it were 0, your betas would never change. But choosing a value for this is important. Conjugate gradient is another technique. It's mentioned in the supplemental reading. It usually works better, but it's harder to implement, and it doesn't work that much better in my experience. So I think just standard gradient descent works fairly well most of the time, especially in very high-dimensional cases. Okay, so choosing the step size is actually fairly important. So let's think about why that is. So let's say that this is your objective function. Looks something like this, and so this is the objective function that you're trying to optimize, and this is your parameter. And so again, just 1D for now, because it's hard to think about higher dimensions, but this holds true for higher dimensions as well. So if your step size is too small, then you just never get anywhere very quickly, and you just slowly walk, and it's okay at first, especially. You can just hobble up this hill, but once you get up here, your gradient is very small, and your step size is also small, and so everything just takes forever, and it takes a really long time to reach the optimum that you actually want to get to. Okay, so what if it's too small? That's what happens. What if it's too large? So what happens then?
In that case, you might, well, if it's convex, then you should still be going in the right direction.
Yeah.
Right? But you might overshoot the optimum.
Yeah, exactly. And so you overshoot it once. So let's say that you start here and you take the gradient and your step size is huge. So you multiply that by the gradient and you end up over here. So let's draw that down. Then we take the gradient there, and then we end up back where we started from, and then rinse and repeat. And we still don't end up where we wanted to get. Ideally, you want some sort of Goldilocks step size. And in fact, one thing that you can do is you can have bigger step sizes at the beginning, where each time you're taking smaller and smaller steps, and you can get to the optimum much more quickly. But to sum it up, the step size is important, and you shouldn't just choose one without thinking.
Could you also, so for example, if you choose the wrong step size, just to retry it, starting at the same position over and over again with different step sizes?
Yeah, so I mean, it doesn't really matter where you start because this is convex, and so having a step size that changes over time sort of is analogous to that.
I guess that would be more relevant for non-convex examples.
Yeah, exactly. So some other issues are knowing when to stop. So you typically need some threshold, and so once your betas stop moving very much, you basically say, okay, I must be fairly near the optimum because the gradient is very small. The gradient is near 0. I should stop once it gets below 10 to the negative 4 or something like that. Another problem, a more serious problem, is what if beta just keeps getting bigger and bigger and bigger? One property of the logistic function is that it takes arbitrary inputs, and so if you move beta over and you had good weights before that matched your data, then making those weights a little bit larger will just make the probability of y given x, assuming that you're getting everything right, just a little bit higher. And so beta will just grow as big as it wants, and you won't necessarily know when to stop. So what we do is we basically add just a little penalty term saying the betas shouldn't get too large. So this is our original conditional probability objective, and we just add in something that says, all right, the conditional probability is good, but you can't let your betas get too large. And so this is called regularized conditional log likelihood, and we've added in another parameter here that basically controls how much we value the conditional probability versus the penalty for the weights. Okay, so another challenge is that our data sets are often very large. And they don't necessarily fit into the memory of a machine, or our data are changing or streaming over time. So in those cases, it's very hard to compute the true gradient. And in the true gradient, you're averaging over all of the observations. So remember, we have the sum over all of the examples. That's hard to do when your data don't fit on a single machine. So what if we approximated this expectation? So we're computing this gradient over all of our data. What if we computed this just from one observation? So that obviously is somewhat noisy, but one way to think about this is the problem of getting to a particular location in the real world. So let's pretend we're living in a pre-smartphone world and you wanted to get to Union Station, and you had no idea what direction to go. What would you do?
I would ask random people.
Okay, so...
Or people who I thought might know.
Okay, so you walk up to a person and you ask which direction is Union Station, and then you start walking in that direction.
Right.
So in particular, what you would not do is you would not set up a survey of all of the residents of Colorado saying that I'm at GPS coordinate AB, what is the direction that I should go to get to Union Station? And so that's sort of the analogy. So if you're computing the gradient over all of your data, you're basically asking everyone who has an opinion, which direction should I go? Whereas stochastic gradient descent or ascent is basically just asking one random person, which direction do you think I should go? So in the real world, you can have the same problem as logistic regression. You can get someone who gives you a wrong answer and points you in a wrong direction. So what happens if that happens in the real world?
You go to the wrong place and then you ask someone else.
Yeah, exactly. And hopefully, on average, you will find more people who are knowledgeable and give you good advice about which direction to go than you get people who are completely clueless. And the same thing holds here, that even though you're much more likely for any individual data point to get a wrong gradient, averaged over many of them, over multiple iterations, you can get to Union Station faster than spending all of the time building a survey to ask everyone in the state of Colorado how to get to Union Station. Another piece of this is that when you're starting out, when you're in Boulder and you ask someone how to get to Union Station, it doesn't matter if they point slightly, if they point east instead of northeast. Just as long as you're heading away from the mountains, you're making progress towards getting to Union Station. So very early on, when you're far away from Union Station, the direction that people are pointing doesn't really matter so much.
So is it typical to use just one example as opposed to multiple random examples?
Right, and so that's an excellent question. And when you use multiple examples, that's called mini batching, and so that's a very common technique that people use. I don't think it makes that big of a difference, but it really varies on the application, and so when you want that last little iota of performance, sometimes using mini batches and changing the mini batch size does help.
So as you climb up the hill or down the slope, as the case may be, you might use more examples to direct your path.
Oh, I actually don't know of people varying the size of the mini batch. I think that can be mostly accounted for in the step size and changing the step size. And so as far as I know, people don't vary the mini batch size that much. Right, and so then your update becomes even simpler. And so your update just depends on, so for a particular dimension, you just look at the value of that dimension for the example, and for that example, what label it had. And so now your update becomes much, much simpler. And notice this term here. If y agrees with this, you don't change your value very much, but the more disagreement you have, the bigger the gradient is, the more you change your weights. Yeah, which makes intuitive sense. And we'll talk through some examples in class. So there are some theoretical things that come into play. How fastly you get to your answer, how quickly, sorry, you get to your answer depends on the convexity of the objective, so how smooth it is, how quickly it changes, and how close you want to get to the optimal answer. And you can actually get better bounds for convergence if you change your learning rate, your step size over time, and you also let the step size vary along the dimensions, because some features are more frequent than others. So the is not very useful, and you shouldn't use, you shouldn't change the very much, but less relevant words or less common, less frequent words might be very useful. So if you see marzipan, that may let you know, oh, I'm talking about food in this case, and you can have a larger step size for those examples.
Do you know when you've reached the optimum?
You can prove some things about that, but it's hard to say what exactly the optimum is, because there are, especially when you're on a computer, because there are numerical issues and things like that. Yes, you know when you're in the region, when you're in some epsilon ball around the optimum, but to be sort of nitpicky, there's no precise way to represent the optimum on the computer because that is a real number, and computers can only represent rational numbers, and so with probability 0 you have the optimum. But you can get close to the optimum. Okay, so in class, again, bring your questions on gradient ascent for logistic regression. We'll work through a simple example of updating our weights,